This talk is going to be a little bit technical, and I will try to explain everything, but feel free to see us after the talk as well if you have any questions or if you want to see any of the code. First of all, I'm Soroush. I worked as a principal application security engineer for Bentley Systems, and I've been in security for more than 2 decades, doing mostly web application security and code review. Today, I'm talking with Pedram, who is the CEO of SecTeam, and there are our Twitter handlers. If you want to give us a follow, we would be thankful. So today we are going to start talking about ToolShell. So the story behind ToolShell is it is a chain of 2 vulnerabilities which were exploited in Pontoon, Berlin. And the researcher got $100,000 by exploiting this vulnerability. It was a rare vulnerability because it exploited an authentication bypass in SharePoint. Normally, the remote code executions that we have with SharePoints are all authenticated, but this one could be exploited by unauthenticated user, which was actually very interesting and at the same time very dangerous. The problem that we had here was the initial patch that Microsoft released was bypassed, which made it all interesting because the bypasses were quite simple. So why is the name ToolShell? The name ToolShell comes from the page that was vulnerable. It was toolpane.aspx that was affected. It could be exploited by unauthenticated users to perform a deserialization and get remote code execution. In my point of view, it should have been called toolpane because it was just too painful to watch, especially after the patch. So here are the vulnerabilities. We had 2 vulnerabilities. One of them was an authentication bypass. It exploited some sort of like legacy feature in SharePoint and managed to reach the restricted endpoint. And the other one was an insecure deserialization using web parts. So web parts in SharePoint can be used for basically creating pages and stuff. And so they can contain some serialized objects, and that was exploited by the researchers to get complete control over the SharePoint server. So which SharePoint servers were affected? All of them. All the on-premise SharePoint servers were affected. 2019, 2016, 2013, and we will talk about 2010 later on. So before I start the presentation, let's just start by showing you a demo, like very early on. And if the demo god is with us, we will be successful. So this is what I'm going to do. So I'm going to send a curl request to the SharePoint server and exploit it. But before that, here is how we generate the payload that goes inside the request that we are going to send. We use a tool that is called Visonet. Visonet.net is the website for that tool. And then you can run it like this to get the payload. Here is the result. And this is the payload that has been generated. As you can see here, I have this exploit class 2.cs, which is a C# application. And in that one, this is the code. What I'm saying is add this header to the response. And also I have some commands to execute, like who am I, hostname, ipconfig, and quite easy stuff. But this code is going to be executed on the server. So let's go back to this. So first of all, let's just send a normal get request using curl to that toolpane.aspx to show that this should not be actually accessible to us. So as you can see, we received a 401 unauthorized, which means that this page requires authentication. And now let's send this one, which does bypass authentication, and then at the same time deliver the payload to the server, deliver that C# code in a serialized object that when deserialized is going to be executed on the server. So let's just send this curl command here. It's a big one because the payload is quite big. So when we send that, as you can see here, we have our headers added. Here is the header that we had added, NDC Manchester 2025, and then we have the username, who am I command, host name, and the IP config, etc. So this was basically what happened on the server. And if I show you this in a web proxy to show you the HTTP request that it sends to the server, basically it looks like this. You send this request to the server, and you basically get a response from the server. Either so this one should this I am hitting the patch server at the moment. I need to point to the vulnerable server and send this request. This is exactly the same request that the kernel sent. So the result should be exactly the same, but more colorful. So here, as you can see, the header has been added, and we have the result of code execution. So now you see that an unauthenticated user, because I'm not authenticated, managed to run command on the server, which makes this issue quite dangerous. And just to show you this as well, while I am in Burp Suite, if I change this to a patch server, which is like 166 here for me, so I am just going to get unauthorized because Microsoft patched it, but this patch could be bypassed. And this is the same server. I'm sending very similar request, but changed a little bit. And if I send that, I get, as you can see, RCE again and remote code execution. Now let's talk about what happened there. Here is the timeline of this vulnerability. So this was exploited on 16th of May 2025 in Pontoon, Berlin. They got the prize. Then 8th of July, 2 months later, Microsoft released a patch for this vulnerability to address the issue. On 14th of July, there was this X message or Twitter message that people were talking about the exploit. Somebody shared a screenshot. And then we saw some GitHub projects coming up with some sort of exploits. And on 18th of July, the mass exploitation of this vulnerability started. And there were some state-sponsored attacks there as well. If you read the news, it was very big. And it hit a lot of infrastructure, a lot of organizations, which was quite bad. And then also on 18th of July, there were rumors that a new variant of this vulnerability is being exploited, not the actual original issue, but the patch bypass. Between 19th and 22nd of July, Microsoft released a few patches to address servers 2019, 2016, and 13. I have to look into see if the 13 was patched, but I think it was. And then they started writing about it, like government advisories were published. There were a lot of GitHub POCs, and none of them were mentioning the bypass. None of them included the bypass. But also Microsoft released something on 22nd of July and said, on 7th of July, we have realized that the attackers were scanning SharePoint servers for toolpain.aspx. We think that the exploitation started 1 day before the patch. So that was quite interesting. So it basically, there were a lot of controversies behind this vulnerability. So how this issue started being exploited before the patch. The other thing was, like, Microsoft knew about these attack vectors, even about the bypasses. Why didn't they address them, like, back in 2020? And why the first patch was so basically so naive, like you could just bypass it. I will show you. So, but then we are not going to talk about this. But that is why it became bigger and bigger in the media, and they were all talking about it. Today, we are going to show you the issue, what the issue was, and then show you the bypasses. We are not going to go deep. I'm just going to show you a very kind of like brief overview them. And then I'm going to show you how we ran some generic models in AI to find the vulnerability and to see if they can find the patch bypasses. So here is the technical shallow dive. It's not a deep dive because obviously it is a bit complicated. So I got this dreamland from the researchers' blog post. They said, we found this, this function that could do deserialization. We were very interested, but we needed to have an authentication bypass, and then we found this. And so if you trace it, and then they're like, oh, and if we do this, we will land in dreamland. And that was quite interesting. So they found a way to bypass the authentication partially to do what they want to do. And here is what they did. They found out if they set the referrer header to a sign-up page, then they kind of get away with authentication, and they do not need to be authenticated to reach to what they want to reach. Something interesting was that referrer header was parsed as a URI. I will talk about it later, why that was also an issue when we talk about the bypasses. So if we think that this was designed for legitimate kind of like sign-out flows, but we still don't know why it is there. And in order to reach that dreamland, in addition to the referrer header, they needed to have three other conditions, basically, in the request. One of them was that display mode had to be set to edit. The other one was that the URL had to start with something and end with something. And then there was another parameter in the post request that had to be exactly as that. Also, I should mention that the toolpaint.aspx, during its life cycle, it checks for authentication, but not on init complete. It is like on load. So if you hit it directly, even if you bypass the authentication without the deserialization issue, you still are going to get unauthorized, but you have bypassed the authentication. So here is the request. We sent this request in Burp Suite basically earlier. As you can see, the first thing we need to set is the referrer header to what we want, and then we set all those other parameters that we need, and then it will hit where it should in the dreamland. So the question about where the authentication bypass has come from. So SharePoint 2010 had this code as well. So this logic was also in SharePoint 2010 for authentication bypass. However, I could not exploit SharePoint 2010 using this vulnerability. And the reason was unknown to me. One of the reasons was like the deserialization also payload wasn't there. The gadget that we needed wasn't there. That doesn't mean that SharePoint 2010 is not vulnerable. It is vulnerable to RC, but using another CVE, which won't be patched because it's out of support. So the patch of auth bypass. So bypass of auth bypass, basically. This was the blocker that Microsoft introduced after the patch. So they were like, if request.path ends with toolpaint.aspx, we ignore the cases, block it, say this is not good. But how can we bypass it? Add a slash just after .aspx, and then you will bypass it, right? But then there were workarounds. Microsoft also came up with defender rules and other stuff to put on servers, so it would block your request. Let's show you the workarounds. Yes. It was exactly like that. So the workarounds are like this. So they were like, look at the referrer. If it has this in the referrer, if it has this in the URL, then deny it. The problem was, I told you earlier that when it was parsing it as a URI, that is actually a good opportunity to have a directory traversal pattern. So you can have like \a or /a, it doesn't matter, and then /. And then it's like you don't have it anymore. So if you put those things there, you bypass that defender rule so that it's like it's not there. Some WAFs were looking for display mode edit in the URL to deny the request, but you could actually put it in a body with a different parameter name. This was the actual, so when I was investigating the issue myself, I didn't know the display mode edit should be in the URL. I was using the other parameter because I was reviewing the code myself manually in a different way. So when the public exploit came, I compared it with my exploit, and I was like, my exploit is different. But then again, when the patch came and I bypassed the patch, mine wasn't caught by the workaround. So I was like, okay, so this is quite interesting. Also, there are other things with .NET. Like in .NET Framework, you can have cookieless. So cookieless is basically, essentially, is this thing that you can have in the URL instead of your session cookie. From ASP.NET Framework applications, they won't see it. They won't see that it exists. It's that slash parenthesis s and then x that you see in the URL. I don't know if I can highlight it here. Basically, that part of the, okay, my mouse is on it. So that part is basically the part that will be ignored and won't be seen, but WAFs will see it and will say, okay, this is not /15 /toolpane.aspx anymore, so we don't care. Let it go. And also, you can have request encoding. Of course, you can. So here is the off-patch workaround bypass. So basically, this bypasses the patch and also bypasses the workarounds. Slash has been added after toolpane.aspx to bypass the off, and then I have added other stuff to the request to make it look different. But that will bypass all the workarounds, which is good. So we bypassed authentication, but is that good enough? Actually, the answer is no. If you do not have deserialization to work, even if you can access that init complete event in toolpane.aspx, it doesn't matter. Because then, in the end of the day, it's just a partial off bypass. So in order to basically make it workable, we need to also bypass the deserialization, the insecure deserialization patch. So what was the insecure deserialization? The researcher who exploited in Pontoon Berlin found a very interesting way to bypass a filter introduced by Microsoft. So the gadget was known, but there was a filter to block it. So they realized that if they wrap that gadget in a list, the list is allowed, and it can go through the filter and can bypass it and can exploit it. So this was their deserialization payload. This was the payload that was released publicly. So this was before the patch, and patch 1 stopped this from working. The way they did it was to remove this Microsoft performance point scorecards client to say it's untrusted in web.config. The way you can bypass it is very complex. You add a space character after scorecards, and that will bypass it. And I'm not making this up. This was actually, it wasn't a new thing. Back in 2021, there was another SharePoint vulnerability that actually exploited this by using trailing spaces. You could have trailing spaces after scorecards in the namespace, in the end of the namespace, or before and after a scorecard client in tag prefix. Both of those could bypass the deserialization patch. So authentication was bypassed using a slash. Deserialization patch was bypassed by a space character. That was quite interesting. So I made that joke, and I was like, yeah, so much space character. So, and I told you that you can also encode the request. It is possible. I'm not going to go into the details. There are other basically materials in the internet to show you this. But I've encoded this request using IBM 500. From a WAF point of view, it's completely unknown. But from ASP.NET point of view, it's exactly the same request that I was sending before. So it doesn't matter. It decodes that IBM 500, and then it all goes through. And then I have my remote code execution. So we wanted to experiment with this to see if, for example, AI can find this vulnerability. This is the workflow that we followed. We installed SharePoint servers, Active Directories and stuff in our lab. Then we started the data collection. Data collection was not just files in the SharePoint directory, it was also files in .NET Framework, the file of .NET Framework from GAC. Then we performed some normalization on the config files to make sure they match each other, that are coming from different versions. And then we performed some data cleaning to make it easier to compare and to remove things like PNG files or things that do not matter. And also, they were like, when the version was changed in a directory, we renamed them to some sort of like unique name so they can be compared. And then we performed the compilation phase of unique managed files, so they can be also compared. And then we use then we perform the patch diff using git diff instead of beyond compare, because we wanted AI to review them rather than human. And then we started our experiment preparation, and then we ran the AI prompts. So all of what we did can be found in this GitHub repository. So all the code, from gathering the data from SharePoint server, from the registry, from all those different directories, to normalization, to the decompilation, to the patch diffing, and all the prompts that we have for our AI, and a step-by-step execution process, and also the result of our AI. The only thing that it doesn't have is the SharePoint code and the compiled code and the actual diff, because it contains some of the Microsoft code. So I will have a barcode to this in the end of the slide, so you can scan it if you want to basically have those. There are a lot of PowerShell files there, and the whole project has been wipe coded. Not saying it was easy, but it has been wipe coded, and I had to probably more than hundreds of commits to it, and it wasn't bad quality commits, I would say, because I had to review them all one by one to make sure it is doing what it is doing. And so one problem that I couldn't resolve was to remove the noise from the diffs. I found it too difficult and too time consuming. I need to find a way to do it using a diff. In Beyond Compare, I have a script, and I can do it manually. It's easy to remove the noise that introduces simple things that change, like a number, we don't care. But then in Git diff, I couldn't do that. So, and these are the AI models that I used during this experiment, the Cloud Sonnet and Cloud Opus 4.5. Opus came during the research, so I had to still use the Sonnet during that. And then we also used Codex Sonnet. With Codex, the problem that we faced was like when we reviewed the research result, we realized that different models were used in Codex. It was just selecting them randomly because we had like this basic subscription. And so we were like, okay, that's fine. It's too late to change it, and also too expensive to use 5.1. But still, it was very interesting. So the challenges that we faced in this research, I think, are also important. We wanted this experiment to be repeatable. We wanted someone else who downloaded that GitHub repository to also be able to repeat it. So I made sure that all the steps are actually coded there and all being explained. And also, we wanted all the AI agents to be able to use the same kind of like prompts, the same kind of like way, so they can be compared. Crafting effective prompts was also a difficult task, because we had to start with the simple prompts, then make it basically bigger and bigger, and then we had to ask AI to make it more concise, make it better, and AI started cheating by giving itself hints in the middle of the prompts. Like, the hints sometimes were very subtle, but after we reviewed the results were too good to be true. Like, it was like 100% success. It was like, no, this is not. This doesn't make sense. Then I was reading the prompt, and in one sentence, for example, it was like, also check for any quirks, in parentheses, for example, white space. No, you don't give yourself hints like that. And so I had to remove those things. I have to make sure they are all correct. And also, it was a little bit expensive, so we had to manage the cost. That's why I used cloud mostly, because I could afford it. And the other problem that we had was like, these ToolShell vulnerability chain weren't the only vulnerabilities that were patched. There were also another CVEs that were patched, and AI was finding those things all the time and was complaining like, this is the vulnerability that you wanted. And I was like, no, it wasn't. So like, there was another deserialization there, but it was authenticated and patched at the same time. So when it was analyzing the code, it was keep finding that. It was like, ooh, look at this shiny thing here. That is what you want. And I still don't know what that vulnerability is actually, but for sure it is in one of those results that AI has come up with. Like, at least there are some hints to it. But it was keep going through some rabbit holes. It even found like an open redirection like vulnerability there. I tried it and it worked, and I was like, fine. I didn't know it. Yeah, these kind of things, so that's why we performed this experiment, because we wanted to see how effective this is. So I defined these experiments as like with 3 experiments, and then I discussed it with Pedram, and he agreed that like we need to come up with some sort of like variants as well for them, so we did that. So in experiment 1, we have the discovery phase. We only give it the patch diff and like the code itself, but we don't tell it what vulnerability have been patched. We don't give it any Microsoft advisories. We don't give it nothing, and we ask to not search in the internet, to not do any kind of like, do not use your knowledge or whatever. Just look at the code and see if you can find the vulnerabilities. Basically, in experiment 1, it's mostly like when you want to find an end day as a reverse engineer. Experiment 2 mostly is like when you're a developer, you have patched a code, and you know where you have patched this, and you want to make sure the patch is good. So we were telling it like, this is the exact patch. Look at it, see if it is bypassable. And then in experiment 3, we wanted to dynamically test it. So we gave it the exploit in Python, and we were like, change this exploit. These are the diff, these are the code. Change it and see if you can bypass it, and test it against our server. So there were these 3 experiments that we ran. So in experiment 1, we had 3 variants. In the variant 1, which was a little bit different than variant 2 and 3, it was kind of like we only gave it code and diff, nothing about anything. And it had to come up with a solution. It also had 2 flow. In one flow, we had 3 prompts. One of them was initialization, the other one was coverage, and the third one was removing false positives. The second one, I merged 1 and 2 together because I wanted it to basically to see what would happen. And then I had the false positive removal. I will show you later that the second flow, interestingly, worked better. I don't know why. But it's just an experiment. So variant 2 and variant 3 are a little bit similar. So we give it, in the variant 2, we give it Microsoft details of like what the vulnerability that they wanted to patch is. We don't show it where the patch is. It needs to go and find out how Microsoft has patched this vulnerability. You know there is like this deserialization. Go and find out how Microsoft has patched it, what the vulnerability was. And in the third one, we also gave it like previous research that has been done on SharePoint. Also any social medias, like posts that were there. All of these are in that GitHub repositories, by the way. And then we ask like to go and find, to see if it worked. So here is a result of the experiment 1, variant 1. This is when we gave it nothing other than diff and code and said, go and figure out what the vulnerability was, what the patch was, if the patch is good, or something like that. As I said, like we had 2 flow. The version 2 that you can see in the screenshot on the right side is where we merged that first and second prompts together. And on the left side is when it had 3 steps. Interestingly, most of the times it was finding the deserialization gadget being removed in the web.config or the other config files. And it even found that there was an authentication bypass somewhere. It didn't know exactly how it's being exploited, but it found out like this is toolpaint.aspx that is the affected page, which was good. So I would probably, if I want to do end-day research, I would run this like 5 times, and then after that 5 times, I probably have the vulnerable endpoint in there, and then I can go and only look at those things. And in variant 2 and 3, when we provided Microsoft data and also the previous research, it obviously found a lot more, because now it knew that there was an authentication bypass. Now it knew that there was a deserialization exploitation. And as you can see, most of the times it got it right. I don't know why in the last experiment, Codex couldn't find the deserialization. Probably because it used a bad model or a weak model, like maybe GPT-4. But then the other cases, you can see the improvement of what happened there. So with that details basically here, if as a reverse engineer, I want to develop my own exploit, I will use this data, I will look at that code, and I will say, okay, so now based on this, how can I reach this function and how can I exploit it? So experiment 2, static analysis. In this, we only had one variant. We gave it the exact patch location. We were like, okay, this is the C# code that has been patched. This is for authentication bypass. See if you can bypass it. The same for deserialization. Deserialization patch was just saying that this gadget is not trusted anymore in a config file. So the result was like this. It didn't find any bypass for deserialization. And the reason is obvious, because there was no parser. It didn't know about that white space in the parser is the actual bypass for it, because it was just looking at the web.config, and it was like, okay, what are other basically gadgets here that I can use? It was just replacing it with other similar gadgets to see if it can bypass it. It even, it was very interesting that it went through that length of finding new gadgets, but it couldn't find any new gadgets. But then, as you can see, still we had more than 50% success with finding auth patch bypass. So it was like, yeah, add a slash after toolpaint.aspx, and you have the bypass, which was good. And then we started experiment 3, which was dynamic analysis to hit the SharePoint server directly. And with this one, we had two challenges. One of the challenges was like when we started this, the deserialization required authentication. And so if we wanted to find out if the deserialization can be bypassed, we needed to somehow bypass the authentication for it. And we either could provide a username and password for it to log in, or we could just enable anonymous or form-based authentication on SharePoint, which we did. It was the easiest. If you use anonymous or FBA on SharePoint, you don't need authentication bypass. So all those SharePoints that were exploited without any authentication bypass were exploited because they were accessible by anonymous users, or they had form-based authentication, which is quite normal, rather than having like a pop-up of in your browser to say enter user and password. The other challenge was that with authentication bypass, it always responded with 401 unauthorized. So no matter what we did, it always came up with that response, because at some point in the life cycle, it was checking authentication. But before that, it was hitting where we wanted it to hit. So we came up with two solutions for it. One solution that I'm proud of, but I didn't use, was to use DN spy on the server to put a breakpoint just after the authentication. So whenever it was bypassing that authentication bit, or in the event that we wanted it to hit, whenever it was hitting that line, it was waiting there. So then I was telling AI, whenever you see a long delay of 30 seconds, that means success. The only problem with that one, and that is why I didn't use it, that it makes you a single agent. Like you can only use a single agent. You become single-threaded, because you have to work for a request and then send the next one and then send the next one. You can't run multiple agents against it, which makes things slow. The other thing that we found was like, we obviously bypassed the serialization first, and then we were like, okay, now that deserialization has been bypassed, just use that, and with our deserialization, we have this header added to the response. So whenever you see that this header has been added to the response, that means you have bypassed authentication. And here's a screenshot of like how we basically set the breakpoint in the code on the server side, and when it was hitting that, that meant authentication bypass. So when I tried it with Gemini, even back in July, when Gemini was like 2.5, it found the bypass just by dynamic testing, by manipulating the URL and sending it to the server. And it was like, as you can see, the request timed out. So now that means we have a success, so which was good. But then I had to go on the server and click continue, and then again come back to that breakpoint if there was another one, and it was painful. But yeah, it worked. So here is the result of experiment 3. Initially, when we didn't give it anything on 3.1, we didn't give it a previous research, anything, just the exploit code, and saying, change this. We want to see if you can bypass it. Interestingly, one of the test cases, I thought it's going to just come out as like 000. But one of the test cases found the authentication bypass, and I was like, that is interesting, because that's something without having any data. And then when I gave it the previous research, obviously, the deserialization became 100%. The reason for that was it was a new thing. In 2021, somebody talked about trailing spaces for bypassing something in SharePoint, and AI picked it up and used it. And then one of them, again, just found the authentication bypass as well. Now, to just say the lessons that I learned personally from the static and dynamic analysis was to always share tech-specific quirks and known security issues with the AI. That means, for example, in ASPX, tell the AI that, look, this is .NET framework, so if I put a slash there, if I use cookie-less, if I do this, if I do that, then I can still hit the same page. So just remember these things. The same thing can happen with quirks with Node.js or other technologies, or like on Apache or something like that. Then always summarize your inputs separately to save time and tokens. That means, like, I had this research here, all HTML files, I converted them to Markdown, and then from Markdown, I created a summary, another Markdown page, and in that summary, then I had, like, this is the bypass, this is the exploit code, these are the details, but very briefly, and then putting the file name there as well. So whenever AI was thinking that I need this, then it was opening that file and was reading it. I found it a lot better than just giving it all the files, because it was just bypassing some of the test cases, it was not testing it. And then I was telling the agent later in the second phase, recheck your result, make sure you have done all the tests, and then that improved the result for me. And I also, I was like, in the final phase, we had this, like, remove the false positives. That was good because there were a lot of false positives in the result, and we didn't want to go through all of those. So there was this one issue when we were running AI against it. Sometimes it was going through a rabbit hole of things that it was thinking that it's a vulnerability, and it was going deeper and deeper and deeper and deeper, and never coming back. And then in the end, it was like, I didn't find anything. So I'm thinking whenever that happens, for example, when it was like, what if we keep this referrer, but then point to another ASPX file rather than toolpain? And then it was pointing at all the ASPX files in SharePoint, and it was just going non-stop like that. And then maybe you can exclude these things, and then it can become a lot faster and better to see if you can find something else. Maybe some of those files will be affected, of course, but then if it doesn't find anything and it is wasting a lot of time, just exclude that. Also, if I had fed the static analysis to the dynamic analysis phase, I'm sure the results would have been much higher, because then static analysis found that authentication bypass quite easily and missed the deserialization. But in dynamic testing, we found deserialization quite easier, but we missed the authentication. So if we combine these together, we will get better results. Another thing that I had problem with was with the dynamic testing, that it was keep reading the code instead of doing the dynamic testing. It was making assumptions that weren't correct either. It was like, it's too simple to just put a white space here and bypass it, so I'm not going to test for that. Literally, it wrote that on the screen one time, and I was like, and then I asked AI, how can I make sure you will test for these things? And then it gave me a better prompt, and then I improved my prompts with that. Yeah, so, and I realized that if I just put the HTTP request there, which I did initially, it didn't find good results because it was using curl, and with curl, it just finds these arguments that it wants to use, and it changes stuff. It messes with the encoding and other things. It changed even one slight character in the middle of base 64, and it breaks the whole thing. So I realized that if I just use this Python code and say, just touch the Python code, do not touch anything else, do not use anything else, then that works better. Also use multi-agent. Do not limit yourself to just one agent at a time. Run it through different agents, and hopefully those will be fine. So I think it is time for Pedram. Do you want to come here and talk? So while he's coming here, I'm just going to give this prompt to this to AI as well. So what I'm doing is I'm running Cloud on a YOLO, like do whatever you want, dangerously. It can even delete my Windows files. Yes, it can. But I'm just hoping that it wouldn't. But it's just for this presentation. I'm running these two instances here. So we will see by the time Pedram is done. Hopefully, we'll get somewhere.
I hope it's not going to delete my slides. I'm talking. So a few takeaways for us. If you're here, obviously, Soroush talked about the takeaways. If you are a reverse engineer and want to do these things, those lessons learned. But I think we also want to connect a little bit to the community here in terms of developers and code reviewers. Again, as we could see, AI is pretty young on finding these things. So always remember the I part of AI, which is you as someone who need to review the results. It is powerful, however, it still is not a replacement. Again, this data of this experiment does show that. However, one of the things that also this experiment shows us, AI is great in finding edge cases. And as you have may guess, edge case is a security vulnerability. So if you want to use AI to identify security vulnerabilities, please do not prompt it with things like this. Find me a security vulnerability in the code, especially if you are not pretty confident whether or not what you get out of it is reliable, because probably the number of false positives that's going to give us is a lot wasting time. However, what we have found is AI is pretty good in fuzzing. Now, for some of you who have done security testing in the past, you know fuzzing is a technique that's been used for, I don't know, hundreds of, not hundreds, like 10 years these days to find situation in a program that result into unhandled or undecided program state. And security vulnerability is one of those program states, and AI is something good for doing it, especially when you are using a type language or when you're using a function that has a clear input and output, because you can provide that function, a specific function to AI, and ask it, find me the edge cases or inputs that result this program or function to an unhandled or undecided state. This will probably find you a lot more bugs than security vulnerabilities, but for sure, you will also come across with some inputs that you may have not thought before. Switching between the models also helps, especially when we are doing code review. One of the things also Soroush mentioned in terms of feeding AI with the previously identified vulnerabilities regarding to the code base that you have, feeding it with the patches that has historically exist with the code, the whole idea of the RAG also helps to improve the detection rate. Now, if you are defender in terms of like you don't have direct access to the code, what are the other takeaways we can learn from this? I want to leave you with effectively two things. Attackers are fast. You could see an example where before even the patch was out, they were doing a large-scale scanning of the SharePoint servers and trying to exploit this vulnerability. So probably you have heard this from a lot of security guys that to patch fast and be fast in patching, that's the main reason behind it, especially for targets like SharePoint that is being heavily targeted by the attackers. So, and I know the pain of patching and improving the increasing the dependency of the code, but when it comes to the situation like that, speed really wins. Last thing, and this is a very interesting mention here, is probably some of you have heard, do not rely on a single layer of defense. Now, one of the reasons that some of those patches didn't work because it was a clear example of Microsoft tried to put a patch in place, a terrible patch, but that was, even if that patch was great, was a single layer of defense. Probably you have heard, and again, do not rely on a single layer of defense. There are many reasons for it. Obviously, with some of the techniques Soroush shows that in terms of using based encoding, using a space, using that and a slash at the end. These are the things effectively attackers are using, or the security researchers are using to bypass those web application firewalls, mostly the pattern-based web application firewalls. But does it mean we should not use web application firewalls? No, we have to use it. Always, and I like to make an analogy here, always think about, anytime come to any system that you build, always think from this perspective of Swiss cheese model. And has anyone heard about this model before? Or at least we have two people, which is great. Now, before I talk about it, this is very interesting because the inventor or the person who invented or proposed this model is actually from University of Manchester. And if I pronounce his name, I think it was James Reason, the guy who did it. And University of Manchester actually did quite a lot of interesting research on safety of the health system, aerospace systems, and manufacturing system. And one of the models that was proposed is a Swiss cheese model. The model is, it gives us a reality how defense or how security, how we should think, assume compromise, how we should assume that the accident will happen. Now, this model was designed for systems within the health, within the manufacturing, within the aerospace. Now, we can borrow a lot of idea from it. And the idea that we can borrow is that any defensive layer that you put in front of your code or system, there is a hole in it. And this is the idea behind it. However, if you include additional layers, and let's assume that each of these defensive layers that you put, let's just say your first layer is WAF, your second layer is rate limiting, your third layer is least privileges, your final layer is a patch that, for example, Microsoft put in the code, 4 layers. Now, we need to assume that all of these layers, they have a hole in it. However, for attacker to be successful, all these holes, as you can see in this picture, need to line up for the attacker to eventually exploit the code. And this model tells us that in reality, a lot of times this will not happen. So effectively, the hazard does not result into the impact because the holes does not line up. So that kind of justifies this theoretical justification that why we should not rely on a single layer, and why even though some of these layers, such as WAF, is not as impactful, they are useful to still to put it in place. And with that, I want to thank all of you for paying attention. This is a QR code for the GitHub code, and we're happy to answer any questions that you may have. Thank you.
Thank you very much.